Lecture 1. AP Chemistry Unit 3, Big Picture. AP Chemistry Unit 3 connects the particle level to the properties we can observe. Matter is made of atoms, ions, and molecules. But the important question is not only what particles exist. The important question is how those particles interact with each other. When particles attract each other strongly, the substance may have a higher boiling point, a higher melting point, or lower volatility. When the attractions are weak, particles separate more easily, so the substance may boil or evaporate more easily. This unit starts with intermolecular forces. Then it connects those forces to solids, liquids, gases, solutions, mixtures, and spectroscopy. So the big idea is simple. Tiny attractions between particles explain large-scale properties that we can measure in the lab. From the tiny to the measurable, this is the heart of Unit 3, Lecture 2. Intermolecular versus intermolecular forces. Before learning the different intermolecular forces, we need to separate two ideas. Intermolecular forces are forces inside a molecule or inside a compound. These include covalent bonds, ionic bonds, and metallic bonds. For example, in an HCl molecule, the bond between hydrogen and chlorine is an intramolecular force. It holds the atoms together within the molecule. Intermolecular forces are different. They are attractions between separate particles, such as between one HCl molecule and another HCl molecule. Intermolecular forces are usually much weaker than the bonds inside molecules, but they are still extremely important. They do not usually change the identity of the molecule. Instead, they affect physical properties. Boiling point, melting point, viscosity, surface tension, solubility, and volatility are all strongly influenced by intermolecular forces. A useful rule is this. Intramolecular forces hold a molecule together. Intermolecular forces hold molecules together in bulk. Chemistry changes when bonds break. Physical properties change when intermolecular forces are overcome. Lecture 3. London dispersion forces. London dispersion forces are attractions caused by temporary dipoles. Even in a nonpolar atom or nonpolar molecule, electrons are always moving. At one moment, the electrons may be distributed evenly, but at another moment, more electrons may be on one side than the other. This creates a temporary electron imbalance. The side with more electron density becomes partially negative. The side with less electron density becomes partially positive. This is called an instantaneous dipole. That temporary dipole can affect a nearby particle. It pushes or pulls the nearby electron cloud, creating an induced dipole. Now the two particles have opposite partial charges near each other. Those opposite partial charges attract. That weak attraction is called a London dispersion force. London dispersion forces are present in all atoms and molecules. They are the only intermolecular force in nonpolar substances. Even though each individual London force is weak, many of them together can have a large effect. This is why nonpolar substances can still become liquids or solids at low enough temperatures. Lecture 4. Polarizability and London dispersion force strength. London dispersion forces become stronger when particles are larger and more polarizable. Polarizability means how easily an electron cloud can be distorted. A small atom has a small electron cloud. Its electrons are held relatively close to the nucleus, so the cloud is harder to distort. A larger atom or molecule has more electrons and a bigger electron cloud. The outer electrons are more spread out, so the cloud is easier to distort. That means larger particles form stronger instantaneous dipoles. Stronger instantaneous dipoles create stronger induced dipoles, and stronger induced dipoles lead to stronger London dispersion forces. This explains important trends. In the noble gases, helium has very weak London dispersion forces, so its boiling point is extremely low. Neon has more electrons than helium, so its boiling point is higher. Argon has even more electrons, so its boiling point is higher again. The same pattern appears in the halogens. Fluorine is small and has weaker dispersion forces. Chlorine is larger. Bromine is even larger and has stronger dispersion forces. As polarizability increases, London dispersion forces increase. As London dispersion forces increase, more energy is required to separate the particles. That usually means a higher boiling point. So for AP chemistry, remember the chain. More electrons and larger size means greater polarizability. Greater polarizability means stronger London dispersion forces. Stronger London dispersion forces usually mean a higher boiling point. Lecture 5. Dipole-dipole interactions and molecular polarity. Dipole-dipole interactions occur between polar molecules. A polar molecule has a permanent dipole. That means one side of the molecule is partially positive and another side is partially negative. For example, HCl is polar. Chlorine is more electronegative than hydrogen, so chlorine pulls electron density toward itself. The chlorine side becomes partially negative. The hydrogen side becomes partially positive. When many HCl molecules are near each other, the partially positive end of one molecule is attracted to the partially negative end of another molecule. That attraction is a dipole-dipole interaction. But polarity is not only about individual bonds. Molecular shape matters too. A molecule can have polar bonds but still be nonpolar overall if the dipoles cancel. Water is polar because it has polar bonds and a bent shape. The bond dipoles do not cancel, so the molecule has a net dipole. Carbon dioxide has polar carbon-oxygen bonds, but the molecule is linear. The dipoles pull in opposite directions and cancel, so carbon dioxide is nonpolar overall. For similar-sized molecules, dipole-dipole interactions are generally stronger than London dispersion forces alone. The key idea is this: polar molecules have permanent dipoles. Opposite partial charges attract. That attraction helps explain physical properties such as boiling point and solubility. Lecture 6. Hydrogen bonding. Hydrogen bonding is a special strong type of dipole interaction. It happens only when hydrogen is directly bonded to nitrogen, oxygen, or fluorine. These atoms are very electronegative and small. They pull electron density strongly away from hydrogen. As a result, the hydrogen becomes strongly partially positive. A hydrogen bond forms when that partially positive hydrogen is attracted to a lone pair on a nearby nitrogen, oxygen, or fluorine atom. Water is the most important example. In water, hydrogen is bonded to oxygen. The oxygen has lone pairs, so one water molecule can form hydrogen bonds with nearby water molecules. These hydrogen bonds explain why water has an unusually high boiling point compared with other small molecules. Extra energy is needed to separate the water molecules because the hydrogen bonds must be overcome. Hydrogen bonding is also important in biology. It helps explain the properties of water, the structure of proteins, and the structure of DNA. But be careful with the rule. Hydrogen bonding does not happen just because a molecule contains hydrogen. The hydrogen must be directly bonded to nitrogen, oxygen, or fluorine. So the AP chemistry rule is simple. Hydrogen bonding occurs when H is directly bonded to N, O, or F, and it is attracted to a lone pair on a neighboring N, O, or F. Lecture 7. Ion-dipole interactions. Ion-dipole interactions occur between an ion and a polar molecule. A very common example is salt dissolving in water. Water is polar. The oxygen side is partially negative. The hydrogen side is partially positive. A positive ion, such as sodium ion, is attracted to the partially negative oxygen side of water molecules. A negative ion, such as chloride ion, is attracted to the partially positive hydrogen side of water molecules. This is why water molecules orient themselves differently around cations and anions. Around a cation, the oxygen ends point inward. Around an anion, the hydrogen ends point inward. These ion-dipole attractions help pull ions away from the ionic crystal lattice. Once the ions separate, water molecules surround and stabilize them. This process is called hydration. Ion-dipole interactions are one reason many ionic compounds dissolve in water. But dissolving depends on a balance. Energy is required to separate the ions in the ionic solid. Energy is released when water molecules attract and stabilize the separated ions. If the ion-dipole attractions are strong enough to compensate for separating the lattice, the ionic compound can dissolve. So the key idea is this: ion-dipole interactions connect intermolecular forces to solubility. Water dissolves many ionic compounds because polar water molecules can surround ions and stabilize them in solution. Lecture 8. IMF strength and physical properties. Intermolecular forces control many physical properties. When the forces between particles are stronger, the particles are held together more tightly. That means more energy is needed to separate them. So, as intermolecular force strength increases, the boiling point increases. The melting point also increases. Viscosity increases because the particles do not flow past each other as easily. Surface tension increases because the particles at the surface pull on each other more strongly, but vapor pressure decreases. This is because fewer particles can escape into the gas phase. Volatility also decreases because the substance does not evaporate as easily. So the key pattern is simple. Stronger intermolecular forces mean higher boiling point, higher melting point, higher viscosity, higher surface tension, but lower vapor pressure and lower volatility. That is why a substance with strong attractions is harder to boil, harder to melt, and harder to evaporate. Lecture 9. Vapor pressure and boiling point. Vapor pressure comes from a dynamic equilibrium between vaporization and condensation. In a closed container, some liquid particles have enough energy to escape into the gas phase. That process is called vaporization. At the same time, some gas particles collide with the liquid surface and return to the liquid phase. That process is called condensation. At first, vaporization happens more often, so the pressure of the vapor increases. Eventually, the rate of vaporization becomes equal to the rate of condensation. At that point, the system has reached dynamic equilibrium. The pressure exerted by the vapor at equilibrium is called vapor pressure. Temperature increases vapor pressure because more particles have enough energy to escape. Stronger intermolecular forces lower vapor pressure because particles are held more tightly in the liquid. Boiling happens when the vapor pressure of the liquid becomes equal to the external pressure. So a liquid with stronger intermolecular forces has a higher boiling point because it needs more energy before its vapor pressure can match the outside pressure. Lecture 10. Types of solids. Solids can be classified by the particles they contain and the forces holding those particles together. Ionic solids are made of positive and negative ions arranged in a crystal lattice. They usually have high melting points because ionic attractions are strong. They are brittle, and they conduct electricity when molten or dissolved because the ions are free to move. Metallic solids are made of metal atoms surrounded by delocalized electrons. Because the electrons can move, metals are good conductors. They are also malleable and ductile, meaning they can be shaped or stretched without breaking easily. Molecular solids are made of molecules held together by intermolecular forces. Since intermolecular forces are usually weaker than ionic, metallic, or covalent network attractions, molecular solids often have lower melting points. They are usually softer and poor electrical conductors. Covalent network solids are made of atoms connected by covalent bonds in a giant network. They usually have very high melting points and are very hard. Diamond and quartz are common examples. The main idea is this: the stronger the attractions holding the solid together, the higher the melting point and the more rigid the solid tends to be. Lecture 11. Structure of solids. The structure of a solid can be ordered or disordered. Crystalline solids have particles arranged in a regular repeating pattern. This long-range order gives them a sharp melting point. When a crystalline solid melts, the ordered structure breaks down at a specific temperature. Crystalline solids can also show anisotropic properties. That means their properties may depend on direction because the particles are arranged differently along different directions. Salt, quartz, and many metals are examples of crystalline solids. Amorphous solids do not have long-range order. Their particles are arranged irregularly. Because there is no regular repeating pattern, amorphous solids often soften over a range of temperatures instead of melting sharply. They are usually isotropic, meaning their properties are generally the same in all directions. Glass, plastic, and rubber are common examples. So the key difference is order. Crystalline solids are ordered and melt sharply. Amorphous solids are disordered and soften gradually. Lecture 12. Liquid versus gas phase. Liquids and gases are both fluid phases, but their particles behave very differently. In a liquid, particles are close together. They have a definite volume, but they do not have a definite shape. A liquid takes the shape of its container, but it does not expand to fill the whole container. The particles can slide past one another, which allows the liquid to flow. Liquids also have low compressibility because there is not much empty space between the particles. In a gas, particles are much farther apart. A gas has no definite shape and no definite volume. It spreads out to fill the entire container. Gas particles move freely in all directions and have much more empty space between them. Because of this empty space, gases have high compressibility. As temperature increases, matter can move from solid to liquid to gas. The particles gain kinetic energy, move more freely, and overcome more of the attractions holding them together. The key idea is that liquids keep a fixed volume, while gases expand to fill all available space. Lecture 13. Kinetic molecular theory of gases. Kinetic molecular theory explains gas behavior using particle motion. The first assumption is that gas particles are tiny compared with the volume of the container. That means most of the gas sample is empty space. The second assumption is that gas particles move in constant, random, straight line motion. They continue moving until they collide with another particle or with the container wall. The third assumption is that collisions are elastic. This means kinetic energy is transferred during collisions, but the total kinetic energy is not lost. The fourth assumption is that there are no intermolecular attractions or repulsions between gas particles. This is an ideal assumption, and it works best when gases behave ideally. The fifth assumption is that average kinetic energy is proportional to absolute temperature. So when temperature increases, the average kinetic energy increases. The particles move faster. Gas pressure comes from collisions between gas particles and the walls of the container. More frequent or more forceful collisions create higher pressure. So hotter gas means faster particle motion, and that helps explain changes in pressure and volume. Lecture 14. Ideal gas law. The ideal gas law connects four important gas variables: pressure, volume, amount of gas, and temperature. The equation is PV equals nRT. P is pressure, V is volume, N is the number of moles of gas, R is the ideal gas constant, T is temperature in Kelvin. This equation is useful because if you know any three variables, you can solve for the fourth. For example, if you know the moles of gas, the temperature, and the volume, you can calculate the pressure, but the units must match the value of R. If pressure is in atmospheres and volume is in liters, a common value of R is 0.08206 liter atmosphere per mole Kelvin. Temperature must always be converted to Kelvin. Do not use Celsius directly in the ideal gas law. The ideal gas law works best at high temperature and low pressure. Under those conditions, gas particles are far apart, and intermolecular forces matter less. So the big idea is simple. PV equals nRT describes how pressure, volume, moles, and temperature are connected in an ideal gas. Lecture 15. Gas law relationships. Gas behavior follows predictable relationships. Boyle's law connects pressure and volume. When temperature and moles are constant, pressure and volume have an inverse relationship. So if pressure increases, volume decreases. And if volume increases, pressure decreases. That is why Boyle's law graph curves downward. Charles's law connects volume and temperature. When pressure and moles are constant, volume and temperature have a direct relationship. As temperature in Kelvin increases, volume also increases. Gay-Lussac's law connects pressure and temperature. When volume and moles are constant, pressure and temperature have a direct relationship. As temperature increases, gas particles move faster and hit the container walls more often and more forcefully, so pressure increases. Avogadro's law connects volume and moles. When temperature and pressure are constant, adding more gas particles increases the volume. The key idea is that changing one gas variable affects the others in a predictable way, as long as we know which conditions are being held constant. Lecture 16. Partial pressure and Dalton's law. In a gas mixture, each gas behaves as if it is alone in the container. The pressure from one gas in the mixture is called its partial pressure. Dalton's law says that the total pressure of a gas mixture equals the sum of all the partial pressures. So, P total equals PA plus PB plus PC. Each gas contributes to the total pressure based on how many moles of that gas are present. To find the partial pressure of one gas, we can use mole fraction. The mole fraction is the moles of one gas divided by the total moles of all gases. Then, the partial pressure of gas A equals the mole fraction of gas times the total pressure. For example, if gas A makes up half of the total moles, then gas A contributes half of the total pressure. The main idea is simple. Each gas in a mixture acts independently, and the total pressure is the combined result of all those individual gas pressures. Lecture 17. Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution shows how gas particle speeds are spread out. Not all gas particles move at the same speed. Some particles move slowly, some move at an average speed, and some move very fast. At a lower temperature, the curve is taller and narrower. That means more particles are clustered around lower speeds. At a higher temperature, the curve becomes wider and shifts to the right. That means more particles have higher speeds. The average kinetic energy increases when temperature increases. So heating a gas makes the particles move faster on average. The area under each curve represents the total number of particles. If the number of particles is the same, the area under the curve stays the same. Only the distribution of speeds changes. The key takeaway is this. When temperature increases, gas particles do not all speed up by the same amount, but the entire distribution shifts toward higher molecular speeds. Lecture 18. Non-ideal gas behavior. Real gases do not always behave exactly like ideal gases. The ideal gas model assumes that gas particles have no volume and no attractions between them. But real gas particles do have volume, and real gas particles can attract each other. These two factors create deviations from ideal behavior. Intermolecular attractions pull gas particles toward each other. Because of this attraction, particles hit the container walls with slightly less force. This can make the measured pressure lower than the ideal pressure. Particle volume also matters. At high pressure, gas particles are crowded closer together. The actual space occupied by the particles is no longer negligible. This reduces the free volume available for motion. Real gases behave least ideally at high pressure and low temperature. At high pressure, particles are close together. At low temperature, particles move more slowly, so attractions matter more. The key idea is that real gases are most different from ideal gases when particles are crowded together or strongly attracted. Lecture 19. Solutions and mixtures. Matter can be mixed uniformly or non-uniformly. A homogeneous mixture has a uniform composition throughout. That means the particles are evenly distributed and the mixture appears as one phase. A solution is a homogeneous mixture. Salt water is a good example. The sodium chloride dissolves in water and the dissolved particles spread evenly throughout the liquid. A heterogeneous mixture does not have a uniform composition. It has two or more visible phases, and the composition can vary from place to place. Oil and water are a common example. They do not mix evenly, so separate layers form. In a solution, the solute is the substance being dissolved. The solvent is the substance doing the dissolving. Usually, the solute is present in the smaller amount, and the solvent is present in the larger amount. The key idea is that a solution is a homogeneous mixture made when a solute dissolves evenly in a solvent. Lecture 20. Concentration and molarity. Molarity tells us how concentrated a solution is. It describes how many moles of solute are dissolved per liter of solution. The equation is m equals n divided by v. M is molarity, n is moles of solute. V is volume of solution in liters. So the unit for molarity is moles per liter, written as mole per L. For example, if 0.10 moles of sodium chloride are dissolved in 0.50 liters of solution, the molarity is 0.20 molar. Volume must be in liters when calculating molarity. If the volume is given in milliliters, convert it to liters first. Dilution uses a related idea. When a solution is diluted, water is added, so the volume increases, but the moles of solute stay the same. That is why M1V1 equals M2V2. The key takeaway is that concentration tells us how much solute is present in a given volume of solution. Lecture 21. Separation methods. Mixtures can be separated because different substances have different physical properties. Chromatography separates substances based on how they interact with two phases. The stationary phase stays in place. The mobile phase moves. In paper chromatography, the mixture is placed on the baseline and the solvent moves up the paper. Different components travel different distances. A substance that is more soluble in the mobile phase travels farther. A substance that is more attracted to the stationary phase travels a shorter distance. Distillation separates liquid mixtures based on boiling point. The mixture is heated. The component with the lower boiling point vaporizes first. The vapor travels through the condenser. Inside the condenser, the vapor cools and changes back into a liquid. Then it is collected in the receiving flask. Chromatography is useful for small amounts of dissolved substances. Distillation is useful for separating liquids with different boiling points. The key idea is that separation methods work because substances behave differently under the same conditions. Lecture 22. Spectroscopy and Beer-Lambert law. Spectroscopy uses light to study matter. Different types of electromagnetic radiation interact with substances in different ways. Microwaves can cause rotational transitions. Infrared radiation can cause vibrational transitions. Ultraviolet and visible light can cause electronic transitions. This means spectroscopy can give information about molecular structure and identity. The electromagnetic spectrum also shows an important trend. As wavelength gets shorter, frequency and energy increase. So ultraviolet light has more energy than visible light, and X-rays have even more energy. Beer-Lambert law connects absorbance and concentration. The equation is A equals epsilon BC. A is absorbance. Epsilon is molar absorptivity. B is path length. C is concentration. If path length and molar absorptivity stay constant, absorbance increases as concentration increases. A darker solution absorbs more light, so it usually has a higher concentration. The key takeaway is that spectroscopy helps identify substances, and absorbance can be used to determine concentration.